So, welcome to this week's Origins Colloquium. It's a great pleasure to welcome Georges Menet to give the talk this week. So, Georges received his PhD, was it 1990, I think, from, uh,
Yes,
was it EPFL or working at
it was
Geneva?
Geneva. I did
Geneva.
my master in in EPFL and PhD in Geneva.
Uh-huh. And, well, has been a has stayed in that area and been a professor since I think about 2006, as I recall. Uh, Georges has led many aspects of development of our understanding of massive stellar evolution and the development of the Geneva Code, which is a world-leading code to help us model the evolution of massive stars. And since massive stars touch on so many areas, there's relevance to everything from gravitational wave signals being found to the elements being seen at high redshifts, early galaxies and globular clusters, to, of course, the massive stars we see locally. So it's a great pleasure to welcome you, Georges, to tell us about selected topics on rotating massive stars.
Thank you very much, and thank you very much for your invitation and to give this seminar by Zoom. So indeed, I will speak about a few topics on the physics of rotating stars. And before to begin, I would like to pay credit with my collaborators who have helped me in the past years to reach some of the results I will present today. So I have chosen to speak about four topics. The first one is a very general one. I would like to remind you what are the challenges in making massive star models. The second one will be to give you a little bit of a flavor on how we incorporate in 1D models the effects of spin rotation. And finally, I will speak about two topics on which we are presently working now, which is first the case of boron depletion at the surface of B-type stars, which is a fantastic test for the physics of rotation in massive stars. And the last topic will be the origin of extremely iron-poor stars, the carbon-enhanced metal-poor stars. So let me begin by saying a few words about the challenges. As Jonathan has just said, I think that we are living in a stage of a golden age for stellar astrophysics. At the same time, stellar astrophysics is a very old topic, which has reached a quite mature state. But on the other hand, I would advocate that it is still a topic very well in the front of today research. As has been already mentioned, if we want to know what are the progenitors of the biggest explosion in the universe, the gamma ray burst, we have to know how massive stars evolve. If we want to know how close binary black holes, which can merge in a duration less than the universe age, we need also, to some extent, stellar evolution to know which stars produce black holes or neutron stars. What are the origins of the R process elements? So many topical problems are related indeed to massive star evolution that are to some extent the main driver of the evolution of the galaxies. What are the main challenges? I have listed five of them here. The first three were already present when I began my research 40 years ago, my PhD 40 years ago. And the last two were known already, but there was no much models, including the effects of rotation and magnetic field, which is not the case today. Let me say a few words first about each of these topics. Actually, what makes a star a relatively simple object is that for most of its lifetime, it is at hydrostatic equilibrium, and this allows to make a lot of simplification. But on the other hand, what makes the stars a very complex system is the fact that they host many hydro and even sometimes magneto-hydrodynamical processes. Convection, as you know, is a very complex phenomena, and especially to know what are the limits of the convective zone is still an open question. This limit, the limit of the core, for instance, of the convective core, determine the lifetime of a star. And so it's a very important feature. The mass loss, of course, allows the stars to have a chemical feedback in case the mass which is lost has been a little bit processed by nuclear burning inside the star, but it can also contribute to the mechanical feedback by putting momentum into the interstellar medium. All the stars lose mass at a given point in their evolution. The low mass star probably only at the very end of their evolution, when they become planetary nebulae, for instance, or during the ascent of the red giant. Massive stars, they undergo mass loss all the time, at least at solar metallicity, beginning with the main sequence phase. One of the difficulties with the mass loss is of course, that we cannot really directly observe it. We have to observe the spectrum of the star and for the shape of the line induce a mass loss. So there is a lot of theory in this kind of, let us say, deduction of mass loss rate. Moreover, we see only the star at a given stage of its evolution. So we don't know what was the mass loss before and what it will be in the future, which of course is needed for stellar evolution. The multiplicity is a big topic. As you know, most of the massive stars are born in multiple systems that are, let us say, tight enough for each star to feel some gravitational force from a neighboring companion. And of course, this tidal interaction can produce deformation of the star, can, in the most extreme case, produce mass transfer, sometimes engulfment of one of the objects in the envelope of the other, leading to a process that is called the common envelope scenario, which is so important for the closed binary black hole. But today, I will mainly speak about rotation and magnetic field. Not only each of these topics could be the topic of one seminar, but they are interacting between them. Convection, as I said, has a drastic impact on the lifetime, but also on the position of the star in the Hess-Russell diagram. This position impact the mass losses. The mass losses remove not only mass, but also angular momentum and impact rotation. Rotation can trigger in radiative zone, for instance, or even convective one, magnetic fields by some dynamo process. The magnetic field at its turn, when it is in the exterior of the star, can slow down the star by magnetic braking. The rotation changes the tidal force in a closed binary system, and the tidal force changes the rotation of the star because, of course, tidal force allows some angular momentum in the orbit to be transferred to the star, or inversely, to take some angular momentum from the star and to put it in the orbit. And all these processes interact in order to impact the lifetime, the track in the Hess-Russell diagram, and so on. There are also some fundamental physics like the nuclear reaction rates, the neutrino emission, the opacities, and the equation of state, which of course intervene into the stellar models and on which we have to rely on either laboratory measurement or computations. Okay, these are for the challenges. Now I want to say a few words about the physics of rotation. A very immediate point when we speak about rotation, of course, if we consider stars as sphere of gas and we imagine they rotate faster and faster, they will be deformed, so they will become oblate. And if we take one layer, one isobaric layer inside such a star, the temperature will depend on the colatitude along these isobaric layers, simply because the gradient of temperature will not be the same along the rotational axis, which is where the star is shorter, than along the equatorial plane where the star is more extended. So you have variation of the temperature along these isobaric lines, and so one can wonder, how is it possible to describe by 1D model a situation that is at least at 2 dimensions? And the trick is the following one, actually. What is possible, or what can be, I would say, can be shown also, is that the temperature variation along typically an isobaric surface remains very modest, at least if you are not extremely high rotation. So it means that each of these deformed isobaric layers can be we, we can attach it a mean value of the temperature. It's possible from this mean value then to reconstruct a 2D, I would say, figures by retaining the first order term in a development with Legendre polynomial. I will not go too much into the details here, but let us say by linearization, it's possible to have variations of the temperature in a 2D models. So actually what is important to understand is that the stellar structure equation that are the usual one as those in non-rotating models have been modified in order that they gives for each layer the value of this mean temperature or of this mean density. And from this mean value that can be extracted from the solution of this system equation, it's possible then to reconstruct a 2D image of the star. So we can say that we compute what Jean-Paul Sein said as a 1.5D models. So it's not 2D, but it's not 1D exactly. This rotation has many effects, and as I said, it deforms the stars, change its hydrostatic equilibrium value configuration. It has an impact on the way the mass is lost by the star. It may trigger magnetic fields amplification by dynamo effects. But the most important effects that I would like to underline here is the effect on the transport mechanism, transport of angular momentum and of chemical species. As you know, the transport of angular momentum is important because it determines how the star is rotating internally. You can expect that during the main sequence, for instance, the core is contracting, the envelope is expanding, so you will have some gradient of omega inside the star, the core rotating faster than the envelope. Any angular momentum transport will tend to, or let us say, we in general tend to reduce the contrast between the core and the envelope. Okay, I will come back to this point in a while. And of course, this distribution of omega inside the star will trigger instabilities that may transport chemical species. And this chemical species transport is, of course, a key process to impact the evolution of stars. Just how do we incorporate these transport processes inside a star? Here I will take as a simple example convection, just to go from something that is well known to something that is less well known, the transport by rotational instabilities. So to some extent, if you want to introduce a transport processes in a star, you have first to identify the instability that is responsible for this transport. Typically, in a convection, if we take the example of convection, convection is a thermal instability. As you know, a bubble, when it is slightly displaced from its equilibrium position, becomes hotter than its environment, and so will continue to go up. This is a thermal instability. Now, what are the conditions for this instability to occur? As you know also, in a star, there is a maximum temperature gradient. It's like the pile of sands. You cannot make a pile of sands which is steeper above some critical limit, because above this limit, the sand will roll down until a maximum slope is built. In a star, it is exactly the same. The temperature gradient will be destroyed until a maximum temperature gradient is built, which is the adiabatic one. And then you have to know to figure out how the process transport energy, angular momentum, the chemical species. For the transport of energy, as you know, in the interior of a star, the adiabatic gradient describe the temperature gradient inside a convective core. The angular momentum is supposed to be transported very efficiently. It's why in most of the models in convective zone, omega is constant, which might not be correct, but this is the way we are doing now. And the chemical species are homogenized. So the same composition is supposed in the whole zone covered by convection. So we have the whole process which is set up. For another instability that is now one of the instability we are considering in rotating models, it is a bit the same. We have first to identify the instability. And in the case of the shear instability, we shall consider this instability not in convective zone, because anyway omega is a constant, and this instability needs differential rotation to occur. So this will occur in radiative zone. And in radiative zone, as you know, in stars, usually there is no mixing. They are quiet phase, nothing happens. An element that is at a given position in this radiative zone will remain in this position unless there is an instability. So if you have two layers rotating differentially, you have turbulence between them that may produce some mixing. Actually, you can see it a little bit like this. If you look at the kinetic energy of a system with two layers rotating differentially, you look at the kinetic energy of the system. Then you suppose that by some mixing, you obtain a uniform velocity for the two layers, and you compute the kinetic energy attached to this uniformly rotating system or uniform velocity system. You will note that the system with differential rotation has a higher kinetic energy than the one with the uniform rotation. So we have that the differentially rotating system as a kind of excess energy with respect to the uniform one. And this excess energy can be used to mix the material. This is the instability. The criterion to mix the material is that this excess energy is enough to bring some material which is down and to bring it up against gravity, for instance, in a star. So you need to have sufficient energy in this excess energy for the instability to develop. And this is given in this kind of physics here by what we call the Richardson criterion. Then, of course, you have to figure out how the energy is transported. In this case of the circular instability, the time scale for the instability is much longer than the Kelvin-Helmholtz time scale. It means that during the ascent of a bubble, for instance, there is ample time for the temperature to be equalized between inside and outside the bubble. So at the end, there is no energy transport by this process. But that you can have transport by chemical species, transport of angular momentum, and you can describe it by a diffusive equation. In the present day, we can say that there are two big families of stellar models. The models which I will call non-magnetic models, and the models that can be described by magnetic models. The non-magnetic models are based essentially on a paper by Jean-Paul Zahn in 1992. Jean-Paul Zahn started or wanted to find equation describing the effect of two main instabilities. One is the shear instability that I have just described now, and the other one is the meridional current instability, which is actually an instability that has a thermal origin. As I mentioned to you, when the star is deformed, become a plate, the temperature is not the same along an isobar, and you will have some blobs which are hotter than their environment, and so they will go up, and blobs inside the star that will be cooler, that will go down. And this buoyancy force, due to this thermal imbalance, will drive a large-scale meridional movement, which is meridional circulation. In the non-magnetic models, this process, the meridional current, is the main driver for the transport of the angular momentum, while the mixing of the element is transported mainly by the shear instability. In those models, you expect to have differential rotation because, as I explained, the core, due to the contraction of the core, is rotating faster than the envelope. Meridional circulation will not be able to much change this situation. They will, but not much. So you keep differential rotation. And since you have differential rotation, you have shear, and you have that the efficiency of mixing of the chemical elements, which scale with the gradient of omega, will occur. In case of magnetic models, you have a very different situation. Actually, this model is based on a theory that has been proposed by Hank Spreut in two papers in 1999 and 2002. And more recently, Jim Fuller in 2019, Patrick Enberger in 2022 have proposed some variation, let us say, of the idea of Engelspreut. Actually, the idea is to say, okay, we start from a very small, typically radial magnetic field. This field is winded up by rotation. It produces a toroidal component. And when the toroidal component reach a given level, it becomes unstable by the Taylor instability. It's an instability that transforms part of the toroidal field in a radial component. And then you continue to wind up the radial component and so on, producing a toroidal, and you amplify the field at very high value. Actually, you can forget the initial value of the magnetic field. Whatever you take, it's so large, the amplification factor, that really it does not matter. So in magnetic models, we don't have to give an initial value for this magnetic field. We directly go to the stationary case where a kind of feedback allows to obtain a saturation situation. In those models, the magnetic instability is very efficient in transporting angular momentum. And we have that it will produce, in most of the case, very flat omega value in the all stars. And because it's very flat, there is no longer differential rotation, shear, and so the chemical elements are transported by meridional circulation that time. So we have solid body rotation and an efficiency of mixing of chemical element that depends on omega and no longer on the gradient of omega. So in the published literature, you have models or library of models using sometimes the non-magnetic physics, sometimes the magnetic physics. In general, the stellar models can handle both. And so you have plenty of choice between these two families, let us say. You can ask, but what is the physics that appear to be the most favored when comparisons are done with observations? If we take as observed constraints the constraints obtained by asteroseismology, or by helioseismology. Helioseismology, of course, is for the sun, asteroids for the stars. And in that case, these techniques allows, by probing the oscillation of the stellar surface, to infer the rotation inside the star. And this has been done for the sun, for subgiants, for red giants, for many low mass stars. We can say that most of what has been observed is much better reproduced by the magnetic models rather than the non-magnetic one. The non-magnetic one predict too large contrast of rotation between the core and the envelope, while the magnetic models produce a much efficient transport of angular momentum, which is more in line with what is given by the asteroseismology of low mass stars. For the massive stars, the situation is a bit more complex, and this is the point I would like to discuss now. But I don't know if I have time. I would like this is a side remark before I go to the discussion of boron, because it may be important for those of you who use rotating models. The meaning here is to say, what I want to say here is that when you use rotating models, there are a few points that are interesting for you to check in the paper that present the physics of these rotating models. Typically, I show you here the equation that describe the evolution as a function of time of the angular momentum. So you have on the right two terms. You have a terms where omega, of course, is angular velocity, and u in the first term on the right side of the equality, the u term is linked to the radial component of the meridional current. And it is what we call an advective equation. The last term, the second term on the right, is a diffusive equation. And the D here can include the shear diffusion coefficient. It can include, in magnetic models, the diffusion coefficient linked to the magnetic instability. This is a bit busy plot, but I will show you exactly what to look at. Actually, you have here on the right a plot which shows the logarithm of the angular velocity as a function of the radius inside a star of 15 solar mass, beginning its evolution at nearly 200 km per second. This is the equatorial velocity on the zero-age main sequence at a metallicity that is 0.012, so very near the solar one. What is represented here is omega, the angular velocity as a function of the radius at the middle of the main sequence. So when the mass fraction of hydrogen in the convective core is around 0.35. When you resolve the advector diffusive equation, you obtain this solution, the solution that I have underlined with a very broad black line here. Now, interestingly, many models account for the effect of meridional currents, but they account it, describing it by a diffusive equation. So they approximate the advective nature of the meridional circulation term. They approximate it by a diffusive equation. And in our code, we can do the same. And if we do the same, we obtain an extraordinarily different solution. We have a much flatter profile. This is the same physics, meridional current, shear instability, but a different numerical approach. Or maybe here I would say numerical physical approach. I must say that by essence, the transport by meridional current is advective. So it should not, in principle, be described by a diffusive equation. As you know, diffusion always tends to smooth any gradient. So it transports always from where there are a lot to where there is less. While advection can act in both ways. It can smooth a gradient, but it can build a gradient too. So it has a much more complex physics. And this we can see here the effect where we have a much stronger differential rotation when we resolve the advector diffusive equation. Just a point here, of course, we can also in this kind of models, which is one of the Geneva models computed by Adam Griffiths 3 years ago, we can implement the magnetic physics. And we have the black line, which corresponds to exactly the same line as before. The red line corresponds to exactly the same physics as the non-magnetic models, plus one magnetic instability, which is the magnetorotational instabilities. And the green line correspond, let us say this one, correspond to the Taylor-Sprout instability. So you can, and then the nearly same solution is obtained when we use Taylor-Sprout plus magnetorotational instability. What is interesting here is that in case in the non-magnetic models you resolve the transport of angular momentum by a diffusive equation, you have nearly no difference when you include magnetic field. Because when you include magnetic field, you obtain nearly the same profile of omega as the one you had already obtained without magnetic field. Finally, just to mention this paper by Devesh last year. Actually, here I present only non-magnetic models. So there is no magnetic models in this plot. But even if you stay in the physics of non-magnetic models, resolving the advector diffusive equation, you have still some freedom in the way, or you have still some freedom in choosing which expression for the shear diffusing coefficient or for another coefficient, which is the horizontal diffusion coefficient. Actually, I had no time to say that before, but in the Jean-Paul Zahn theory, you have, of course, that the instability along a radial direction, a shear instability along the radial direction, has to struggle against gravity. It has to bring some material down to put it up. The horizontal diffusion is rather an instability that occurs along an isobaric surface. And along an isobaric surface, the effective gravity, which is the sum of the classical gravity diminished by the centrifugal force, this effective gravity is always perpendicular to the isobaric surface by the hydrostatic equation. And in that case, any shear along an isobar has no need to struggle against any gravity. There is no longer the need for that. And so it's a very efficient transport. And you have different expression for this horizontal transport as well as for the vertical transport. This will not change the way omega is changing inside the star, because omega in those models is mainly transported by meridional currents, which is taken in the same way, but it may change the chemical profile. What is shown here is the evolution of the effective temperature as a function of the mass fraction of helium at the center of the star. So in this upper part here, you have the main sequence, which occur, of course, at a high temperature. It's for 15 solar mass stars at solar metallicity. And during the main sequence, the helium in the center that begin at 0.25 or 0.26, I don't remember exactly here, increase up to nearly 1, where it is the end of the main sequence, where all the hydrogen has been burned. And at the end of the main sequence, you can have, in the case of B, a very rapid crossing of the Hertzsprung-Russell gap. And then you have the decrease in the center of the helium burning when the star burns its helium as a red supergiant. So in the case of B, you have this situation. But now if you change the expression for the diffusion coefficient, you can have a very different situation. You see, let us look at the red line. You have the end of the main sequence. You begin to cross, but around 4.15, sorry, the star remains at that position, burn helium, and will join the red supergiant stage only when it has only a 0.2 mass fraction of helium at the center. So you can see the crossing here can be different, and this has an impact on the blue-red supergiant ratio, for instance. Just to show you the right plot, where it is shown the profile of helium inside the star. So you have, this is the helium mass fraction as a function of the mass. At the center, you have the convective core, which is here at the beginning of the helium burning phase. And you can see that the one that evolved the more rapidly to the red is the one that has the more helium in the zone between around 5 solar masses here. And it is where the hydrogen burning shell occurs. If by the mixing processes you put helium in the region where hydrogen is burning, you have to decrease hydrogen because, of course, you cannot, if you add one element, you have to remove another one. So hydrogen is less abundant in this hydrogen burning shell. If it is less abundant, it has more difficulty to compensate for the loss of energy by the surface through the luminosity. And so the star will contract. It will contract, and this will release enormous amount of energy, part of which will be used to inflate the envelope. And this is why the star, in that case, becomes very rapidly a red supergiant. Okay, so now I will just take 5 minutes to speak about boron, and after I
That's
will
fine.
stop.
That's fine. Yeah.
Fine? Okay. So boron is a very nice element. It's a bit the lithium of massive stars, you know. It is an element that is fragile. It is burnt by proton capture at temperature around, let us say, 6 million degrees. To give you some comparisons, the lithium is still more fragile. It is burned at nearly 3 million degrees. The helium-3, on the other hand, is more robust. It needs 14 million degrees. And the nitrogen, not to be destroyed, but to be produced in the core by CNO process, requires temperature around 17 million degrees. I show you here a profile inside a 12 solar mass stars, which is rotating, initially rotating at 40% the critical velocity on the ZAMS. And you have actually this line here, the black one, dotted and dashed one, which correspond to boron 11, and the green one, boron 10, two isotopes of boron. And you can see that at the beginning of hydrogen burning, most of the boron has disappeared inside the star because it's too hot. It is destroyed by proton capture. If you don't rotate, it will remain like this, the whole main sequence, unless there is a little bit of mass loss. But otherwise, it will remain at that value at the surface. On the other hand, when the star is rotating, you will produce a transport of this boron inward, where it will be destroyed. And finally, you can see that in the middle of the main sequence, the mass fraction of boron has decreased and has nearly completely disappeared at the end of the main sequence. So the question is it observed this? And the answer is yes. What is nice, it is, so here we have a 12 solar mass, so it's for a hot star, a B-type stars, and it is at the very beginning of the main sequence that it occurs, between panel A and B, we are still at the beginning of the main sequence, and we have already an effect which is important. So could it be explained by another process than mixing? Maybe mass loss, but the mass loss is too small. A 12 solar mass stars has typically a mass loss rate of 10⁻⁸ solar masses per year. So you need 100 million years to remove one solar mass. But if you look at the profile, you can see that the plateau of boron remains over, let us say, half a solar mass. So you would need 50 million years to really begin to see the gradient of boron. But the lifetime of such a star is only 18.5 million years. So the mass loss is probably not a good way to produce a boron depletion. Now, is it the case that we can invoke closed binary evolution? But closed binary evolution is a bit the contrary. You produce too much mass loss. You can see here in this system that has been computed by Wehlstein, where you have a 12 and a 7 solar masses. The 12 solar mass during the first mass transfer will lose 2/3 of its mass in a very short amount of time. So, and if you lose 2/3 of its mass, you will remove all the boron-rich part, and you will even see nitrogen-rich layers. So probably binary is not the good way of explaining the boron depletion. You have here some plots where we show some abundances recently collected by Jean et al. 2024, and plotted over this observation are models computed by Luca Asiatani, who was a student by Patrick Eggenberger. These plots show the boron surface abundances as a function of V sinus I. You have models with different initial mass. It's 9, 12, and 15 solar masses, which are indicated here. And you have different initial rotation. So it's why you have many times the same triplet of mass, because you are looking at more and more rapidly rotating stars. The evolution in such model, in such figures, is that during the evolution, you have that the surface velocity is in general decreasing, so you evolve to the left here, and boron is depleted, so you go to the left and you go down, except maybe at the very first part of the evolution, where you remain more or less constant in velocity and constant in boron abundances. But at a given point, you go to the left and you go down. The colors along the line represent the gravity at the surface of the star, which decreases as a function of time, of course, because the star is inflating. You have on the left the non-magnetic model, the non-magnetic models, so without magnetic fields, and you have on the right the model with magnetic fields. And if you look in more details, the discussion in the paper, but we can a little bit guess by looking at the points and how they compare with the position of the tracks, we can see that the models with magnetic fields are better than the non-magnetic one. Here, however, we have only plotted observation for relatively fast rotating stars in the sense that it's stars with a V sinus I larger than 80 kilometers per second. And we have plotted only stars which are evolved, which have a log G below 3.9. So for these stars, magnetic models appear better. On the other hand, if we do an analysis, and this is not shown here, but if an analysis has been done by Luca Giattani, it seems that for the slow rotating stars, typically those with a V sinus I below 50 kilometers per second, the non-magnetic models would be better than the magnetic one. Interestingly, this last point is, let us say, in concordance, in agreement with this observation of a beta Cephei stars. Beta Cephei stars are massive stars, not very massive, typically around 9 solar masses. And this one, this specular beta Cephei star, has a very slow surface rotation, 2 kilometers per second, like the sun, if you want. And you can see here only, I would say, profile of omega as a function of the radius obtained by different models. So there is no observation. The only thing that has been observed, or let us say that has been deduced by asteroseismology, because for such a slow rotating stars, it's possible to infer the internal rotation by asteroseismology thanks to the mixed mode and to the pressure mode. We know that we have indication that the core is rotating 3.6 times faster than the surface. And you can see here that if you apply, for instance, the Taylor-Sprout theory or the Fuller Taylor-Sprout theory, this is the horizontal line. So we expect to have no contrast. It's flat from the core to the surface. If you use the Taylor-Sprout theory, it's a bit better because there is a gradient of chemical composition that diminish the efficiency of the transport between the core and the envelope. And you have a contrast for the evolutionary stage of the stars, which is the very beginning of the main sequence, of 1.6. If you look at hydrodynamical models, the one with the shear and meridional circulation, you have the red line with a ratio between the core and the envelope of 2.6. It's not perfect, but it's already better than the magnetic one. And the blue line corresponds to a star which has local conservation of the angular momentum, so no transport, just a change of omega by contraction to the core, expansion of the envelope. So we see that here, of course, there are some error bars here that I don't know precisely, but we would be, if we take at face its value, a little bit in between. Okay, so I think that I will stop here. In case I had planned to speak a little bit more about the carbon-enhanced metal poor stars, but maybe we can open the discussion.
Thank you very much, George. So many things were brought up there, and yeah, we can always come to the Kemp stars as well now in the discussion. So questions for George, raise your hands in the Zoom. I have a whole list here. So then let me start if I don't see. So let me go in order. You mentioned, of course, you're using 1D code. Just can you give us a quick summary of the status of actually using 2D codes or 3D codes? You know, what state are they at and
Okay. Yes, actually, what I know at the moment is the following point. First of all, there are attempts to make 2D codes, and the only person I know who is now working on such a code is Michel Riotor in Toulouse, in France, who has created a code called Esther. And it's still a bit difficult to consider it as an evolutionary code. At least when I have looked at this, it was a few months ago. It's still more a code that can be evolved, but in not in the way that we are evolving our stars with very small time steps and so on.
Mhm.
And it's focused on the main sequence.
Mhm.
One of the big success of this code, however, was the prediction of the way the effective temperature is changing between the pole and the equator when the star is rotating.
Right. Well, I was going to
And
ask then, because you said the main approximation of the 1D code is you're assuming the same temperature at a given layer, where
we actually we are supposing that the average temperature, of course, the average temperature is only one temperature per layer, but this is the average temperature.
yes.
And we can have some knowledge of the variation of temperature by making some small development, keeping the first order term.
Okay, because well, you said the temperature gradients are the differences are relatively small from that average, but some processes depend on temperature very sensitively. You know, the nuclear burning processes. So, can you remind us? Are you is that where you expect the biggest differences from a 1D?
No, I don't think, because anyway, the nuclear reaction will occur in convective zones. And in convective zones, it's a very different story from let us say, the radiative one, because anyway, the mixing of the elements is so large that, of course, you can have some change of temperature somewhere, but the mixing will, in my view, blur a little bit, a lot, the pictures, the details here.
Uh-huh. Okay, then. Well, then we can go to, let's see. Again, I'm looking in the Zoom. If people raise your hands. Now then, let's see. Well, then of course you mentioned the two big divisions of these magnetic models and the non-magnetic models. And as I understand it, then the magnetic models are very efficient at transporting angular momentum. So you end up getting effectively solid body rotation. Um, and then you mentioned in the sun, that seems to be true in the convective zone. My memory of the sun, again, it's years since I took a class on this, is there is a differential rotation. So can you just
Yes.
remind us why, you know, surely that means it hasn't all been erased by magnetic effects.
Mhm. No, it's true. Actually, we know that the convective zone of the sun is not rotating as a solid body. It is more a kind of cylindrical rotation. But it's a bit maybe, I would not say I don't know whether it applies, for instance, to the rotation rate in convective core. In the sun, we have magnetic field, as you said. And the magnetic field, of course, has an impact on this kind of process. But what is interesting is that below the convective zone, you have a small layer which is called the tachocline. And in this tachocline, you have a uniformization of the velocity, of the axial velocity. So the differential rotation that exists in the convective core disappears below this tachocline.
Mhm.
And the radiative part of the sun is rotating as far as we can say, because of course near the core we have no observed constraint. We
Mhm.
should observe the gravity waves in order to probe what happened really in the center of the sun. So we cannot say what happened in the center, but up to, let us say, very near the center, it's flat.
Mhm. But
Flat.
why in the convective zone do we not also transport angular momentum efficiently with magnetic effects?
Um, this is a good question, but I have not the answer of that, I must say. Uh, it is, first of all, it's an observed fact. Should we, I would say that we know from observation and from helioseismology that indeed the rotation rate in the convective zone is not uniform as it is below in the radiative one. But I guess that for the sun, the magnetic field here plays a central importance. Of course, when I say that in our models, we suppose that the magnetic field produce a very efficient transport that makes solid body, it's a magnetic field that is produced by the star itself by what we call the Taylor-Sprout dynamo. The dynamo of the sun is a bit different. Actually, the dynamo of Taylor-Sprout occurs in radiative zone. Obviously, if there is a dynamo for the sun, it should occur in the convective zone. And here the physics is different. It's not the same process, let us say.
Mm.
It's not a physical process. But I must confess that I don't know so well the details of the physics of this part of the sun.
Hmm. But anyway, in that case, you're saying in the radiative zone, you become a solid body, and then somehow, even though there's still magnetic fields around,
But this is an internal magnetic field. It's not
I,
necessarily the same as the one at the surface, you know.
sure, sure. Okay.
And it's not, for sure, not the same physical principle that is
Mhm.
responsible for
Mhm.
it.
Well, maybe it's a sort of smaller scale eddies or something in the convective zone.
Yes.
Yeah. Okay, then. Let's see. Devesh, you had your hand up if you want to ask
Yeah,
something.
the question following up. Hi, George. Just wondering
Hello.
exactly you kind of answered it, but about this magnetic transport via the Taylor-Sprout dynamo. As the star goes to the advanced nuclear burning stages, I guess, or at least for massive stars, most of it turns convective. So how would this dynamo be effective there? Like, does it really mainly dominate, of course, the main sequence, the longer duration of the star, or like how will it evolve as we go to advanced stages? What would we see? Uh, is my question.
Okay, this is a good question. Of course, what changed during the advanced phase is the structure of the star, which become much more complex with maybe sometimes a lot of intermediate convective zones, as you know. But and also the time that is available becomes very short. So in order to have something that has an effect, you need effects which are very efficient. Um, my record of typically the work by Adam Griffiths, who has looked at what happened in the advanced phase, is that it's not, I would say there are some effects of this Taylor-Sprout dynamo, but probably most of the effect, most of the impact comes from what happens during the longest phase of the evolution. It means during the hydrogen and core helium burning phase. In the advanced phase, as I said, you need extremely powerful and efficient processes in order to occur in very short lifetime, very short time. You can have processes like, for instance, the dynamical shear, which is not a magnetic effects, but dynamical shear can change a bit the zones of chemical composition in the very advanced phase. For the magnetic fields, I must say my record or what has been discussed by the paper by Hayden Griffiths, who look at this advanced phase, is not so much. They are not so much modified by very important effects due to the magnetic field.
Mhm. Okay, great then. Then I had a specific, on your last part, you mentioned the boron, the depletion. Perhaps you could pull up that slide again. You mentioned the data seem to favor the magnetic models, but perhaps I'm just missing something here. Um, there seem to be plenty of data points that are not covered by those tracks on
Oh,
the
yes.
right-hand side, whereas on the left, at least I've got tracks covering the data points. So can you just clarify why you think the right-hand side
No,
is better?
no, I think you are right, actually. There are some points. I would say, um, it's a, how to say that? It's always the case when you make comparison between models and observation, you get not that one model is perfectly working and the other one perfectly non-working. But what you get here by looking at the plot on the right, you can see that, for instance, those points which have, let us say, a log J of 3.7, which are near the white or the blue or light blue, are probably better reproduced by those, this track, for instance, the 12 solar mass track, across the error bar here with at a color which correspond to one of the
Okay,
point, for instance.
I see. I'm comparing.
You see?
I was not
But
comparing color of the point with a line. Yes,
But,
that's right.
but of course, these one, for instance, these one are not reproduced by the magnetic models.
Mhm.
But they are not so well reproduced by the non-magnetic one too.
All right. Now I got you. Yeah.
So, okay,
Right.
let us say that statistically, if you look at the number of points which are better reproduced, the number of points better reproduced by the magnetic models is larger. Let us
Yeah.
say like this.
Okay. No, I got it. Well, great. So then in the last 5 minutes or so, we can come to the perhaps more, the question, either the Kemper question, but I have questions about what you think about nitrogen abundances as well. So generally predicting abundances and yields. Perhaps it's all related to here.
Yes.
So just,
Yes.
yeah.
Um, you mean the production of nitrogen
Well,
by
you could
rotating?
start with the Kemp. Why don't we do what you would
Okay.
first? Yeah.
Okay, so I can just, to be very rapid here, I will skip a little bit the general points, but this is an old plot, but finally it gives very well, it defines very well what we call carbon enhanced metal poor stars. It's a plot where you have on the horizontal axis Fe over H, and of course you go toward more and more, I would say, iron poor stars to the left. Maybe I will do like this. Maybe it's better.
Hmm.
And you have on the vertical axis the carbon over iron. And you can see here a series of stars which are clearly above a kind of plateau defined by the normal carbon-rich stars. You have stars which are at low metallicity, below typically Fe over H minus 2, and which have very high carbon abundances by 1 or 1.5 degs. And you have, of course, some cases which are not so different, like, for instance, the Caphao stars. But you have also this one, which is the Christleb, the Frebel stars, and the most iron-poor star that we know today, I think it's still the case, which takes the record, is the Keller stars. Oh, sorry. So it's at the Fa over H, which is less than minus 7. So you could say maybe it's a population-free stars, but it is not because it's carbon-rich. You can see here the point. It's at a very high level of carbon enrichment, and carbon is not produced by Big Bang nucleosynthesis. It should be produced by some stars. It cannot produce by the star itself because this stars is typically a star on the main sequence of maybe a subgiant stars. There is no way to produce a high amount of carbon. You need to go into the core helium burning phase to produce such an amount of carbon. So there is no way for the star to produce such an amount. It should come from elsewhere. And where does it come from? This star, typically, which is carbon rich, is a low mass star, typically zero 0.9 solar mass stars. So it can live for long. It's a very iron poor. So it has been formed at a time when the interstellar medium was still not much enriched by many generations of stars. And this star, typically a star of zero 0.9 solar mass stars, lives for 14 billion years. So it means that a star that has been born 9 billion years ago is still alive today on the main sequence. And this is a star that we observe and that is carbon rich. A way to explain this, and this is a way that has been a method, or let us say a scenario that is a scenario of many different works by Ken Nomoto, by Tominaga, by Arthur Chopin, is to suppose the following thing. So you suppose a mother star, which was massive stars, the stars of a previous generation of the carbon enhanced metal poor stars. These stars evolved, eject some material, maybe at the end of its evolution in a kind of supernova, and it will enrich a pocket of interstellar material. And from this interstellar material enriched by these mother stars, new stars can be born. And these new stars present at their surface a chemical composition that is the one of the cloud enriched by the massive stars. So if in the frame of this scenario, looking at the surface abundances of these stars gives you an indication of the ejecta of the mother stars, let us say, or at least of the dilution of some ejecta with normal interstellar medium.
And there is some iron present, just very low. Is that right?
Sorry,
There is some iron. Iron is detected
yes,
in the Kemper star.
actually, iron, when we say that these stars are carbon enhanced metal poor stars, actually, this is not a good term because the metal, carbon, oxygen, nitrogen, can be at very high abundances. What is really poor is iron.
Yes.
So we should call these stars carbon enhanced because they are carbon iron poor stars. But the acronym is more
Right.
complicated
But
like
I'm
this.
just saying that there is a finite, I mean, iron is detected in the spectra just at a very
Yes,
low.
yes, absolutely. Iron is detected.
So that supernova should make some iron as well.
It depends. It could be a massive star with an iron abundances equal to that of the star, in which case it will not be a first generation star, but a second generation star, you know? It could be, but it could be also a population-free star that indeed should produce not only the carbon, oxygen, nitrogen, but also produce some iron, but in a very small quantities.
Mhm. Mhm.
And you know, one of the difficulty that in general supernova produce much more iron than the small quantity that is seen into the carbon enhanced metal poor stars. It's why people like, for instance, Umeda and Nomoto has proposed a scenario where you have faint supernovae with mixing and fallback. What does it mean? It means that it's a faint supernovae because you will expel only the outer layers of the stars. But since they considered population-free stars, if you expel only the outer layer of the stars, you have no iron. Iron is produced in the core. So in order to still eject a little bit of iron, you need to bring this iron in the part which is ejected, and this is why they call the model with mixing.
Ah,
You
yes.
know? So you need some mixing at the moment of explosion, some bullet of iron that are propelled into the region which is ejected, and with some fallback so that the more internal part that are also pushed away fall back onto the star, where most of the iron remains locked.
Mhm.
Actually, the model that we propose here can be quite, I would say, could be combined with this idea of Ken Nomoto. There is no problem. It's just the model by Ken Nomoto is more a model of the explosion, while our proposition is more a model for the previous evolution of the star.
Right.
So, so I don't know how much time do I have? 5 minutes or?
Just a couple of minutes if we can. And then
Okay. So the point is that, you know, we have proposed a long time ago to look at massive, fast rotating metal poor massive stars in order to see whether they could be the progenitor, the mother stars. And mixing, of course, induced by rotation is especially important. Here you have some plots where we show the helium zone on the left, the hydrogen burning shell on the right. And during core helium burning, you have carbon and oxygen produced in the helium burning zone, which migrate by rotational mixing into the hydrogen burning one, being synthesized or being transformed, at least in part, in nitrogen 14, carbon 13. But you can have that this nitrogen and carbon diffuse back in the helium core, producing neon 22, magnesium 26, and again, neon 22, magnesium 26 can diffuse into the burning shell, producing sodium 23, helium 27. So this back and forth mixing produces a lot of very interesting nucleosynthesis. And with Arthur Choplin, we are now studying rotating models, looking especially at one element which is fluorine-19. Fluorine-19 is a very complex element because it needs protons and neutrons to be synthesized during the core helium burning phase, where protons have disappeared. Neutrons are still there, but still neutron requires huge nuclear networks to be full because neutrons can interact with nearly all elements. But in these models, some extended nuclear reaction has been accounted for, and so we can follow the synthesis of fluorine in those very metal poor stars, so 20 solar mass stars with a metallicity 10-5. And we can suppose that, so we have only looked at one initial mass stars, one initial metallicity, and we have supposed that all the mass above some mass cut has been expelled. Then we take this mass, we mix it with some amount of interstellar medium material, which is in general 1,000 more massive, typically. And we look at the final composition that we compare with the one observed at the surface of the CMP nose stars. And here you have the results. The different lines here correspond to different initial rotation for the 20, different mass cut, different mixing dilution, and the last numbers here correspond to the chi-square. And the chi-square tell us that the model that would the best reproduce most of the data is the red line here. You can see that the fluorine, which is at z equal 9, is too much produced by these models, you know. So it's not perfect. The other one are okay, but at least we have a model that can reproduce most of the elements and indeed produce fluorine enhancement as observed. Okay.
And the data come from this particular Kemp star, do they?
Yes, actually, the CS29 and so on has been observed by Mura Guzman very recently. It's very difficult to obtain fluorine, and it's why we were very interested here, because it's the only star for which fluorine has been observed in such a very metal-poor carbon-enhanced stars.
Uh-huh.
Then
Very
there
good.
is a second one, but it's just an upper limit.
I see. Very good. Well, we should wrap up the main session now. So let's thank Georges again for a great talk and discussion.
Okay, thank you very much.